Yeah, so good evening, and we'll start the discussion. Uh, so this will be like the last class on metal forming topic. So as you know, this syllabus or the whole course is divided into three parts. First was casting. So first four lectures were on casting. Then we spent about four lectures on forming, metal forming, and then now this is the fourth one, last one on forming. Next one will start, I think, joining processes like welding, etc. But yeah, so today there are different concepts that are or different operations that are to be discussed. You know, like extrusion, then drawing, then bending, you know, and sheet metal operations. So uh, there are a lot of things to be discussed, and then finally we have defects, metal defects, etc. Those things are there. So we'll go one by one, and before actually just yeah, 1 second. Yeah, so see, there are different operations in our you know this thing, uh, metal forming processes. So you can broadly classify them into applications based on this thing. Uh, what you say, type of stresses involved. So, I'll just give you that brief idea so that later on, whenever, because there are some questions in competitive exams where they, you know, ask certain things like this. So, just for the sake of argument, so you can construct a table like this. Here you'll have stresses induced, okay, and on the other side you'll have you know, operations or which forming operations come under this category. Okay, so this is a broad classification. Sometimes they ask such questions, and if you don't know the name of the process or how it works and which type of stresses are induced during that, then it's difficult ones. Sometimes you'll not be able to answer. So first, let's talk about shearing. So as you know, shearing is like a force acting perpendicular to the normal axis or longitudinal axis of your domain or material. So here you have this blanking, punching. Punching is also called as piercing. So these are synonyms. Then you'll have notching. Okay. So again you have trimming. There are some other processes called as shaving and nibbling. So they also come under this category. So these are various metal forming processes where you have shearing stresses. Okay. And second, then you have tension. So tensile stresses or tension, or I'll just write tension. You understand that tension means tensile. So here you have this stretch forming. So this was also discussed in the class briefly, not in detail, because these are there are like wide range of forming operations, and you cannot discuss each and every one. But you should at least know that when I say stretch forming, what type of stresses will be induced in your specimen. Okay. Then you have compression or compressive stresses. So when you say compression, you'll have coining, sizing, ironing, and hobbling. Okay, so these are various metal forming operations. as the name suggests, you basically will compress your workman or specimen. So, if you are interested, you can just Google about each term and you'll get pretty decent descriptions. It's widely available, not like very, hidden or something. And then you have last category, which involves tension plus compression. Okay. So in this category, you have drawing operation. So we'll see different drawings like a tube drawing, bed drawing, all those things are there. Then you have bending. Bending, on one side you'll have compressive stresses, on the other side you'll have tensile stresses. Forming also involves compressive and tensile. Then you have spinning and embossing. So these are operations which involve tensile plus compression. And what happens in competitive exams, they mention if forming, or for that matter, yeah, 1 second. Second, I'll just confirm one thing before telling you, because it's this extrusion process. This also involves multiple stresses, because uh, uh, because you see, we'll discuss about extrusion. So basically what happens, uh, you press something, and on the other side you'll have a small opening and you stretch that wire out. But on the die where you have that hole, there are some compressive reaction forces also. So tension plus compression is also there in extrusion process also. But extrusion process, it's a slightly peculiar idea, because in many competitive exams, when there is only one correct option, if only one option correct, then extrusion process, you should say, induces compressive stresses. Because in some competitive exams, when the paper setter is not that aware of these kind of things, they will just give you four options, and extrusion process, which kind of stresses are there, compressive, tensile, shear, everything will be there. So in that cases, you have to pick compressive, because if you have to choose one, compressive is the dominant stress in extrusion, etc. But it's not like only compressive stresses are present, because you're stretching the wire, right? So there has to be some tensile stresses there. But yeah, majorly or predominantly compressive stresses are responsible for extrusion. So that's why, if it is more than one option correct, then you may have to go for tension plus compression, or even shear also you can consider, because nobody says uh, like if friction is not there, then maybe shear stresses will not be there. But even in that case, in the bulk of the material, there can be shear deformations, right? You never know. So uh, yeah, if you ask me, then tension, compression, shear, friction, all things should be considered, but predominantly compressive stresses are responsible for extrusion process. So this is like a brief introduction, and yeah, after that, let's talk about extrusion processes. So first of all, you know just 1 second. Yeah. So extrusion process. So first of all, what is the uniqueness of these things? you know Extrusion process. So, you should, we'll see this different types, etc. But you should remember the uniqueness, you know. Uh, so this extrusion process can be used for ductile as well as brittle materials. And this is a very unique property or very unique characteristic, because you should have uh, seen by now, there are many forming processes for ductile materials, but for brittle materials there are not many, because brittle materials usually have very small tensile and shear strength. They have high compressive strength, and in extrusion predominantly you use compressive stresses to do the forming. So therefore, you know uh, you can use brittle materials and extrude them, and not all techniques can be used. That one hydrostatic extrusion technique is used for brittle materials. We'll see about that. And other ductile materials, like steel, even steel, stainless steel, cast iron, zinc, tin, all those things, it all can be used. And in sometimes, in competitive exams, they may ask like uh, under what applications, match the column type of questions. So, sometimes they give nuclear rods, nuclear reactor rods can be manufactured by extrusion. Okay, so many a times you will have this match the column or match the pair kind of questions. So if you have nuclear rod option, mostly it is done by extrusion. Okay, and after that there is a classification of extrusion processes. I'll just give you the tree diagram so you can understand what I mean by that. So first of all, it is hot extrusion, and you can have cold extrusion also. See, cold does not mean it is sub-zero temperatures or something like that. Cold just means that uh, you are you are operating below the recrystallization temperature of the material. So then you have two types under hot extrusion. First is direct extrusion, and see, the thing is, and then you'll have indirect extrusion. So these two categories are there. But broadly speaking, under hot and cold extrusion, there are certain things that we'll discuss. But just finish the tree diagram. And cold, you'll have another two set of processes. So you have forward extrusion here, forward extrusion, which is also called as hydrostatic extrusion, and it is used for brittle materials. Okay, because under hydrostatic condition you only have compressive stresses, and all of them are equal in nature and compressive in uh, direction. So failure of brittle material is arrested in those cases. And then you have the fourth category for this is backward extrusion, and it is like a indirect extrusion only. But here you don't operate at higher temperatures. You basically use impact energy to carry out the extrusion. This is a broader uh, classification of various extrusion processes. So you should remember this. If you remember this like this, it is very easy to remember. Okay. And then we have seen what do you mean by direct and indirect. So indirect, you have maybe you can just draw a small diagram. What do? You press. You have a hot material operating above its recrystallization temperature limits, and then you have a die like this, and you basically press from this side. This is like a piston cylinder assembly, and whatever you have material you have, it will go out from this. So this is your die, and this is sometimes called as ram, okay, or piston or plunger, whatever it is. And you have a direction of extrusion parallel to the application of ram force. Okay, but in case of indirect extrusion, it is the ulta thing. Okay, so indirect extrusion, I mean, this was discussed in the class, so I'm not paying more attention to the details. I'll just tell you some characteristics that are useful. So you'll have something like this, and you'll have again one ram will be there, but the ram has the opening in it. Okay, so and you press it like this, but because of the opening out between the ram, so this is your ram and this is your liquid material which comes out in the opposite direction. So that's why this is called as direct and indirect. That's the only difference, nothing major. uh, okay. And sometimes they ask why extrusion processes are used, etc., those kind of things. So you know extrusion process is highly economical, that is first. And another characteristic is this one, brittle wala thing. And you can have size reduction up to 40:1 also. So this is a significant kind of size reduction. If you remember our rolling and all those things, there you would have to have multiple passes for these kind of size reductions. So that is main advantage of extrusion. And coming to the hot and cold one. So basically, this hot and cold, there are some penalties. In cold, you need not have to have high temperatures, so that is the saving. But in cold, you'll have to have apply more ramming force, so that is the penalty. Whereas in hot, you'll need lesser ramming force, that's the plus. But you'll need to, have higher temperature and handling processes, etc., slightly inconvenient in that case. So those trade-offs are there in every category. So you have to deal with those depending on what kind of application you want. Okay. And if you compare these two, this direct and indirect, what happens? You know, direct, indirect. See, basically, uh, in case of indirect, in indirect extrusion, you know, no frictional, no frictional resistance between billet and the die. See, they call this as billet. Okay, so sometimes it is called as billet or whatever, but sometimes they call it as specimen also or material also. But billet is sometimes used, so keep that in mind. Billet and die, due to which 25 to 30% lesser ram or ramming force is required. Okay, so in indirect case, you have requirement of lesser ramming force because of less or negligible friction between the billet and the die. Okay, so that is how it goes. But it's not like, see, if this is the advantage, then everybody would have used indirect, right? It's not like that. Indirect also has some limitations because you know what happens when you are pressing, the material is coming from that side only, so you have to be very careful. Okay. And you know uh, there can be leakage chances, etc., deformations at the stress concentration will be higher at the ram, right? So therefore you have to be very careful. It's not that easy to do the indirect one because you are operating in a hot extrusion domains. Okay. And now let's come to this one, this cold extrusion. So this backward extrusion or impact extrusion used for very soft materials, you know. So soft materials include polymers, cosmetics, all those things are there. Even lead or zinc or tin, those kind of small or lower melting metals also can be impact extruded. And famous MCQ question comes out from this is collapsible tubes. Collapsible tubes are made using this, which are used in toothpaste, cosmetic, and battery shells. Okay, so these kind of applications are peculiar for impact extrusion. And since impact extrusion is nothing new, basically you fill the die with the metal vertically, and then you drop the ram or punch from high altitude, so that the potential energy has, when it impacts on the billet, it will have the impact, and the potential energy, which is converted into kinetic energy, that will come into the converted into the strain energy, and that will have the deformation. Okay, so that's why you can't have hard materials here, because for hard materials, if you want to just deform them by using gravitational energy, you'll need very large height, or you'll need to have a ram or press, mechanical ram or electrical press or something like that, hydraulic also. Okay, and this yeah, so basically I'll just give you some simple diagram so that you remember this. What happens, you have a die like this, consider our toothpaste kind of example. You have a die like this, and you know you'll have some material at the bottom like this, or maybe like this. Okay, you feel it like this, and let's say it is closed from this end. So and what happens, then you drop the plunger or the ram from, let's say, some height, and or 1 second, it should not be, you know there will be some clearance. Okay, so there will be some clearance between the die and the ram or plunger, because that will determine the thickness of your tube. And when it comes down, what happens, when this ram reaches here, or even goes deep into this, you'll have uh, this this surface, or the circumferential volume filled by your soft material. Okay, so the reason why I drew this figure is, here you should remember that the direction of uh, direction of metal flow or material flow is opposite to that of uh, punch or ram. Okay, so this is the kind of thing like you see in the indirect extrusion. That's why it is also called as backward extrusion. And forward extrusion, that is used for brittle materials, also called as hydrostatic. And the reason why it is called as hydrostatic is, you know, it looks similar to what we have in the direct extrusion process, but there is a slight difference here. You know, first of all, you have a brittle material, and between the ram and the material or the billet, there will be liquid, incompressible liquid usually. So you don't have billet occupying the whole thing. Your billet will occupy certain portion of this, so it will be something like this, in a some container or something, and this will be extruded. So what happens, this liquid will exert the hydrostatic pressure on the brittle material from all the sides. Okay, and that's why you have all the compressive stresses there, and you can extrude brittle materials, right? So you do this, and you have this brittle material inside. So that is the difference, or material. Okay, So, not only brittle materials, even hard materials like tungsten. See, tungsten has very high melting point and it's very hard, and it's not very easy to uh, do that. Molybdenum, stainless steel, and other uh, brittle materials. And this phenomenon, in which you basically make brittle material as a ductile material and you extrude, it is also called as pressure induced ductility. Okay, so in some competitive exams, they may use this kind of keywords to determine, to explain, or to match the uh, pair with the hydrostatic extrusion or forward cold extrusion. Okay. And as you can see, uh, there is no frictional resistance here because there is no solid to solid contact, and you know negligible frictional resistance is also one characteristic. Negligible frictional or friction, and it does not require no lubricants, because the liquid that is there itself act as lubricants. So it is also called as self-lubricated method. In all other methods, you may need lubrication, because to reduce the frictional resistance between the die and the billet. But here it is self-lubricated. Okay. So this is the broader classification of these methods, and apart from that, we saw some this formula or something like that. Okay, so you should remember one thing, that yeah, so some things like extrusion ratio, because in some for questions, they will just mention like extrusion ratio is this and that, and then you have to calculate. So A naught is initial cross sectional area before extrusion, and AF is the final extruded cross sectional area. And then you have something like fractional reduction in cross sectional area after extrusion. They typically use small r symbol for that, and it is given as A naught minus AF, the reduction in the cross sectional area, divided by original cross sectional area. So if you separate the terms, you get AF by A naught, right? And one more thing, sometimes yeah, it's okay. So AF by A naught, so that is R is 1 by R. Oh, sorry, 1 minus 1 by R, and therefore you have R, which is 1 by 1 minus R. So these kind of formulas you should remember. If you remember, then fine. Otherwise, you can derive also in the exam, but it will take some time. Okay. And similarly, you have this something called as extrusion force. Okay. So typically denoted by P. It is, there are different formulas for this, but widely used are the simple ones like these, where K is a extrusion constant, R is this extrusion ratio, and very important, this is A naught. So initial cross sectional area. Many a times students forget this and use, they get confused between initial or final cross sectional area. You have to be very careful and use initial cross sectional area. Okay. And I think there was one previous year question on this. Let me just check. Yeah, we'll solve some simple questions, or questions like this. There was a question in which a brass billet is extruded from 100 dia to 50 dia. and the extrusion constant is 250 megapascal. Find the force required for the extrusion. This was the question. This is a previous year GATE question, 2 mark. So you have to use this formula. So P is K naught. K naught is 250 MPa into A naught. A naught will be pi by 4 d square. So initial diameter is 0.1 meter. So that square into ln of r. R, as we know, it is A naught by AF. Okay, so you can remember like this also. It should be always greater than 1. So A naught will be proportional to the square of diameter. So 100 square divided by 50 square. Okay. So that is just 4 times. So ln of 4. And if you plug all these values, you should get P as 2.72 meganewton. So these kind of questions are asked in the GATE exam. So you should remember the formulas and you can solve it. Then before moving on to the next one, there are some these things, extrusion defects. Okay. We'll discuss those. Because there are some metal forming defects, but it is better to discuss them with the this thing, what is it, individually. So in which category, or so for example, in extrusion there are some peculiar defects. In drawing, etc., there will be some other defects. Okay, so we'll discuss such things. So in extrusion, there are some 2-3 defects that you should remember. Okay. First is called as surface cracks. And I mean, everybody knows what are cracks, so that is there. But it is caused due to high temperature. So more probability in the hot extrusion process. High temperature, high speed of extrusion. So if you are rushing or not giving enough time for metal forming, or that grain deformation. And again, high speed also means that high friction. So under such conditions, there is a probability of developing surface cracks. Second, you have bamboo defects. It's again very unique name. In many exams, they just mention that bamboo defects is observed under which metal forming process. So extrusion is the answer. And it happens at low temperatures. So basically in cold extrusion domains or methods at low temperatures due to sticking of metal in die. Okay, so sometimes even if you use lubricant or something like that, since there is what do you say, you are in the cold extrusion regime, so you need proper lubrication, etc. If it is not there, you'll get bamboo defects. And the reason why it is called as bamboo defects is you'll see extruded products like this. It looks like a bamboo when you have extruded. Ideally, you don't expect any surface indenture or anything like that. But in these cases, because of that sticking with the die material, and if you keep on pushing it, suddenly it will leave, but there will be not a smooth surface finish. Okay, and then there is a third one which is called as fishtail defects. Okay. One second. It is also a peculiar thing, but let me just confirm one thing about this. Hmm. Yeah. So, what happens? Uh, I think this was in the notes given by professor also. Let me just check once. Hmm. Sheet metal rolling, forging, or not specific to extrusion. Okay, okay. One second. Yeah. So basically, in this one, fishtail defects. Uh, it's like you know this thing, fishtail. You uh, I mean, it's in the name only. It's fishtail, no? So it looks like a fishtail. So you'll see if when you extrude, you'll see something like this, some defects like this, because they look like tail of the fish. It is called as fishtail defects. And what happens? This happens because of surface oxides or impurities, or you know uh, percolate. So these impurities, uh, you know they don't have any other way to go, so what happens when you extrude, they percolate towards the center of your, towards inner or center central region. And then you basically see some fishtail defects like this. And then there are something called as chevron cracks. Okay. So chevron cracks, oh, one second, what happened, something happened. Okay, so you have chevron cracks, uh, or this is also called as center bursts, so it is nothing but uh, what happens when you have excessive compressive stresses. uh, you know there will be tensile stresses developed at the center, because you're stretching the material from the center, right? So what happens when you have excessive tensile stresses at center line, you see cracks at the center. Okay, and it's these are very difficult to detect. Okay, because uh, at the center, if there is any crack, If it is not at the periphery or the surface, you will not be able to detect them. So usually it looks like this, and it is not at the periphery. Okay, it is at the center line. So these are very hard to detect. Okay, so and this center burst, etc. Then there are some piping defects, etc. But the idea is same only. This piping defect is nothing but again, because of this impurities, etc. It's like a fishtail defect only. So this is again can be looked into as piping defects. Here also impurities go toward the center. So you'll have fishtail kind of things. Okay. So these are the defects associated with the extrusion process. Okay. So this is the uh, discussion about the extrusion process, and then there were some mathematical formulas given by professor. But the similar formulas you again come across in the uh, drawing, which we'll see now. So that's why let's go to the drawing or next topic, and we'll finish those things. Okay. So now we'll go to the uh, drawing. Okay. So you have a wire drawing, uh, and then you have a tube drawing. So we'll see one by one. Most of the things are discussed by professor in the class, but let's see one things. Okay. So uh, let's start with the wire drawing. So now we'll discuss drawing. Okay. So extrusion is done. So now let's go to the drawing. So in drawing, the most common is wire drawing. You have tube drawing, etc. But uh, wire drawing is the most common, or majority of that. So here what happens, uh, you know you decrease the cross sectional area of your wire or the billet or whatever you have, and but finally you will have a very thin dia wire. So usually typically less than 5 dia. So we call it as this thing, you know uh, wire. And if you look at the whole thing, the die that is made up of for this thing, it looks like this. Okay, so there are different zones in the die. It's not a single step kind of a reduction process. So you have something like this. Okay, so the die is having distinct regions. Okay, so maybe something like this. Okay, and similarly you'll have symmetric things on the bottom side. Okay, like this. Okay, so something like this. So this is your die for doing wire drawing, and it has a distinct four regions. So you know so this first one is, let's talk from inlet to outlet. So there are like four regions. This is first, second, third, and fourth. Okay, and this is your die. So this is your die, both from top and bottom, and this is your direction of wire drawing. So basically, you will have a larger cross-sectional area going in, and then the cross-sectional area goes down. And this angle, sometimes this alpha is this again same alpha. It is called as a semi diangle. Okay, and there are these four zones. The first one is called as lubrication zone. So which is just at the entry. Okay, lubrication zone, and what happens, there are different type of lubricants. You have solid lubricants and liquid lubricants, and sometimes no lubricants also. But if you don't use any lubricants, there is a chance that you'll have you know uh, black or burnt color on your wires when you draw them because of the frictional things. Because see what happens, when you reduce the cross sectional area, most of the times you will have a temperature rise because some part of strain energy also goes into overcoming the frictional resistance offered by the die, and that eventually is dissipated as heat. Okay, so that is why most of the times wire drawings you'll have higher temperatures at the outlet, and usually to avoid that you should have some lubricants, and as well as to conserve or preserve the surface texture of the wire drawn. If you don't use any lubricants, first of all you'll have a hot wire at the outlet, and you may have a black or burnt surface depending on how much reduction you have done and what is the velocity, etc. And sometimes in competitive exams they ask some questions like this, if you have no lubricant, black or burnt surface, okay, wire surface. If you have something like graphite, solid graphite, powder. So basically you apply the solid graphite powder and you get dull surface, dull wire surface. And if you apply oil, okay, so different kind of oils, not the single oil, you get bright or shiny wire surface. Okay, so depending on what type of surfaces you want, you can do these things. And before entering into the lubrication zone, there are different things that are done. It's not like you take any material and start wire drawing. It's not how it works. It will, you'll not get a desired surface finish, as well as the defects will be more if you do directly. So, first they do, uh, I mean, here first acid pickling is done. So basically this is, these are some terms that are sometimes thrown in the questions. So acid pickling is, basically removing dust or scale from the surface before wire drawing. Okay, and then after pickling you do the surface coating, lubricant coating. So depending on which type of lubricant it is, if it is a solid one, then you have to do proper coating. If it is a liquid, it's fine, it's okay. And as I said, solid graphite is used sometime. Ferrous hydroxide is used for, especially for stainless steel, etc. You need not remember these things, but it's good to know. Sometimes you can use lime water also. So it's not like only oils are used. Lime water is also used. Not lime water, just lime water. Okay, so these kind of things are there. Okay. Sometimes you use this phosphates, manganese, iron, zinc, phosphates also, so that surface finish is observed without any damages. Okay, and then you have the second zone, which is called as deformation zone. Okay, deformation zone. So actual deformation takes place here, and this sometimes they try to trick students by asking about this semi-diangle. So alpha is semi-diangle, and this is the force for drawing, and this is alpha, or maybe 2 alpha. So this is called as diangle. So what kind of value of 2 alpha should be chosen for This thing is the question. So there is a optimum value. It's not like as you increase the alpha, you'll get lesser force requirement, etc. What happens up to the up to this point, in this region, uh, as alpha increases, F decreases. But what happens if you have excessive alpha? There is a reversed metal flow that happens here, because you can imagine, right? If there is like 90 degrees triangle or something, very small amount of material will go in, most of it will be sent back because of the reaction from the die. Okay, so there is some optimum value. Okay, so that is also sometimes asked. And what is the optimum value? It depends on the material that is being deformed, etc. And what happens then? There is deformation. Anisotropy will be induced in your material. Since surface area is reduced, the velocity will increase because of constant volume condition. And then this third region is called as sizing zone. And in sizing zone, your cross-sectional area is constant, so that the velocity is constant. And basically you keep this sizing zone dimensions slightly lesser than your expected you know uh, dimensions, are more or less constant and kept slightly lower than final desired dimensions. And you get that right, because the fourth zone is uh, nothing but, which is called as recovery zone or elastic recovery zone. So what happens, these are all uh, you know uh, even though you have plastic deformation, there will be some elastic part associated with it. And because of that, uh, this thing uh, you have uh, this for elastic recovery accommodation, and also exit for lubricant, because along with the material, lubricant also gets compressed during these initial 3 or 2 zones. So finally lubricant has to also come out. Okay, otherwise if lubricants gets trapped and all, so there will be surface effects, etc. So you know those are the purposes for keeping the slightly larger exit or elastic recovery zone. So this is the basic about drawing. Then you have again, here also you can have cold and hot and all those things. Sometimes wet drawing is also there. So what they do, instead of applying lubricants before entering, they put all this setup inside the lubricant itself, so that there will be no chance where you'll not have proper lubrication. But again, it's not that good idea, because whenever you have lubricants, there is always chance of leaking, thermal degradation because of temperature changes, blah blah blah. So you'll have to have a lot of things there. Okay. So but yeah, in some cases that is also done. And then there is something called as tube drawing. So you know here basically you'll not have, so basically you'll have wire, you'll not have hollow components out of these kind of dies. To have hollow components, you have tube drawings. I'll just mention these things. Wet drawing, because these are discussed in the class already. So and then you'll have tube drawing. So in tube drawing, basically you are drawing a tube, not the wire. And you basically use plugs or mandrels to have hollow core during drawing. So this is the principle is same. It's just that you introduced one plug or mandrel or something, so that when you extrude or when you draw the material out of that die, there will be hollow core. Okay, the central part will be hollow, which is typically called as uh, this thing, this one, tube drawing. Okay. So then there are some derivations. So I'll just give you the formula. So for wire drawing, you have to calculate the load, etc. So you have a generalized load equation. So how much load is desired or applied, required, or something like that. So sigma d is the load that is desired. Sigma naught, you know, sigma naught is its yielding yielding stress. Okay, and you'll have this 1 plus b by b factor, and then you'll have 1 minus a final divided by a naught raised to b plus sigma b into this a final by a naught into b. Okay, so a final by a naught, in the context of extrusion, what was a final by a naught? A final by a naught is 1 by r. Okay, so here also, if you want to remember in terms of r, basically this af by a naught is 1 by r from our previous discussions, if you want to relate that way. And b is nothing but mu cot alpha. Alpha is semi-diagonal, keep that in mind, not the diagonal. Mu is coefficient of friction, usually we assume it constant. And then the sigma b is called as back pressure or back tension. In some cases that is also given. If it is not given in the question, you just take it as 0, because if there is some back pressure or back tension, you need to have more force. Okay, and then there are some these things, one second. Okay, so then sometimes you simplify these formulas. So let's consider one case where you have ideal conditions. And sometimes when they mention ideal condition, that means mu is 0 and therefore b will be 0, and also sigma b is 0. In ideal case, there is no back tension or back pressure. So your whole formula, typically, see, sigma b is 0, so this second term goes away. There is no issue there. But what happens to this first term? When you put b 0, you have 1 by 0. This ratio becomes 1 by 0, and you and here also you have this b is also 0, right? If you put it that way, so basically this is not a standard formula, so you have to use L'Hospital's rule to find the limit. So after this you need to apply L'Hospital's rule, because you have uh, 0 by 0 form you have. So therefore, when you apply the L'Hospital's rule and you put the limit b tending to 0, in that case finally you should get sigma d equal to sigma 0 into ln of ai by af. Okay, so this is very important formula, because sometimes they ask directly some things like this. We'll discuss about that. So sigma naught is basically its yielding stress or flow stress or something like that, they will give in the question. So just 1 second. Yeah. So let me just check once. So sometimes, or in not sometimes, most of the times they say that neglecting friction, etc. And they will sigma naught is basically called as flow stress because we are having flow deformations, etc. Here, I just want to confirm that once before moving on. Yeah, the mean flow stress basically. So sigma naught is called as mean flow stress. Yeah. Okay, so sigma naught is mean. Okay. So the point is, from this sometimes they ask a very important question, which is, find the maximum area reduction possible during wire drawing process. Okay, so there are, this is a question. There are two parts to this question. First is assume ideal conditions. So basically you'll have mu equal to 0 or frictionless conditions. And second case they can give is when mu is not equal to 0. So under both these conditions, you need to find the maximum reduction in area that can be achieved through this wire drawing process. Okay, so first case, we have already seen this formula, equation star. So, for ideal case, sigma d is sigma naught. An ideal case means mu equal to 0. Sigma naught into ln A initial. So, A initial is basically, our A0 that we are using. So, A naught by AF. Okay, so this can be written as sigma naught into ln of R. Okay, that is also possible, but let's continue. So, in for maximum area reduction, you need to have the drawing stress equal to your mean flow stress. So therefore your ln of A naught by AF becomes equal to 1. Okay, and ln of 1 is nothing but, in that case, your A naught by AF has to be equal to E. E is an E, this value. So basically your final area will be A naught by E. And this E is a standard number, right? So E value is 2.718. So therefore your final area will be A naught by 2.718. And if they want to know the, and it's easy also because we know this A naught by A naught by AF is R, and but what they are asking is maximum area reduction. So basically they want R, and from the previous cases we know that this R can be written as 1 by 1 minus capital R, right? Okay, R is 1 by 1 minus 1 by R. 1 minus 1 by R. So here R is E. So you have to take 1 by E. So that becomes 0.368. So this is basically 1 minus 1 by E. 1 minus 0.368. So therefore R, which is nothing but fractional area reduction maximum, So this is actually R max. This is not any R, it is maximum that is possible. R max is 0.632, right, or 63%, roughly speaking 63.2, but if you can round it off, it will be around 63%. Okay, so this is a very important result. Many competitive exams, they will ask one liners like this. And second case where you don't have mu is not equal to 0. So in this case also the see the criteria is same for maximum area reduction. Sigma d has to be equal to sigma naught. Okay, and our formula for sigma d is sigma naught 1 plus b by b into 1 minus af by a0 raised to b. So sigma b is 0, usually back tension if it is not given, you just assume it as 0. So now when these two are equal, the sigma d and sigma naught, this gets cancelled. So you have two terms. So this b plus 1 plus b goes to the other side, and this becomes 1 minus af by a naught raised to power b, right? And then you can do further simplifications, and what you can do is you can do this 1 minus this thing, right? So af by a naught raised to b will be 1 minus b by 1 plus b, right? So this will be 1 plus b minus b by 1 plus b. So b gets cancelled, it is 1 plus 1 plus b, 1 by. Okay, so now you can take 1 by b powers on both the sides. So you'll have af by a naught as 1 divided by 1 plus b whole raised to 1 by b. Okay. And then this is your 1 by r, right? So therefore you can calculate r as 1 minus 1 by r. So therefore this is r max condition in this case. So that will be 1 minus 1 by 1 plus b whole raised to 1 by b. And here b is actually mu cot alpha. So depending on the values of mu and alpha, you will have the maximum value here. Okay, so like that you have to proceed, and this is a very interesting question. Otherwise rest of the questions are like you know uh, numerical based. So there are some questions like I'll just read one question because we have done such question previously also, so I'll not do it again, but I'll just give you the idea. So what they do is initial diameter is 6 mm, and finally you want the diameter to be 1.34 mm, and or maybe I'll just, okay, 1 second. Hmm. 1 second. See, it is like that number of passes question. We have already done those. Uh, you know, so we can take this question. Okay, so let's take this question. It is a question is, they have given mu as 0.2 and semi-diagonal alpha as 6 degrees, and what they're asking is to reduce the diameter of 6 mm to, let's say, 1 mm what is the minimum number of passes required during wire drawing process? This kind of questions. So this question I mean the question is different. I just modified this. So so here see, you have to understand first of all minimum. So we need to have maximum area reduction per pass, and you have to use this formula, right? So you know that R max, R is nothing but you know uh, this fractional area reduction, right? So A naught minus AF by A naught is your R, and that is maximum for 1 minus 1 plus 1 by 1 plus B 1 whole power 1 by B, and B is mu cot alpha. So let's first calculate mu cot alpha. That will be 0.2 into cot alpha. So cot of 6 degrees Celsius, degrees not Celsius. So if you do that, you should get, let me just check, trigonometry, okay. Okay. So cot of 6 degrees is this 9.5 into 0.2. If you do, you get 1.903. This is 1.903. Okay. So this is actually equal to 1 minus 1 by R also, right? Where R is A naught by AF. I'm just simplifying our life because you'll see. So 1 by R has to be 1 by 1 plus B whole raised to 1 by B. So that will be nothing but 1 by 2.903 raised to 1 divided by 1.903. Okay. So if you do this calculation, what you should get here is, just do it. Okay, so you have 1 divided by 1.903, and here you have 1 divided by 2.903. So you should get 0.571. So if you do the inverse of this guy, you should get R as 1.51. Okay, so what it means that in one pass, let's say after one pass you have A1 cross sectional area, you can have the reduction in cross sectional area maximum as 1.751 times in each pass in first pass. Okay, and we know that we want to talk in terms of diameter, right? So area is pi by 4 d square. So that means d1 square should be d naught square by 1.751. So I have to take square root on both the sides. Okay, so first let's take the inverse, answer inverse. Okay, and then take the square root of new answer. So therefore you have d1, which is the diameter after one pass of drawing operation, which will be d naught by 1.323. Okay, so just for the sake of checking, so if you have 6 as the initial diameter, and if you divide this by this, So 6 divided by 1.323. So you will get the diameter after first maximum reduction, assuming you will get 535 mm. Okay, so like that. So now they are asking after how many number of passes the final diameter will be 1 meter or less than 1 meter. So we have done this, right? So you have to use dn equal to d naught by 1.323 power n, because in each successive draw the diameter will go down by same factor, right? So you can write 1.323 power n as d naught by dn, and here d naught is 6 and we want it to be 1 at the end, so therefore it is equal to 6. And then when you take the log on both the sides, this will be ln of 1.323 in the denominator, right? So if you just do this, ln of 6 divided by ln of 1.323, you get n as 6.4. Okay, and as this we have seen, whenever you have this integer, you have to take the next integer, right? Because you cannot have fractional passes. So therefore you have n equal to 7. So you need at least 7 passes to have reduction from 6 to 1 mm. Okay, and this is assuming maximum reduction per pass. If it is not maximum reduction per pass, you may even need more number of passes. Okay, so that depends. In that case, they will mention some other things. In that case you may have to use this formula. Okay, so this is how sometimes questions can be framed, and you should be able to answer them. And then this formula is slightly modified for uh, you know tube drawing. So for tube drawing, there are two frictional surfaces, right? uh, Two frictional surfaces are there, are observed. So you have similar kind of formula but with slight modifications. And again, I'm that back tension etc, I'm not putting it again, but you understand. So b dash will be nothing but mu1 plus mu2 by tan alpha minus tan beta. Okay, so now this mu1 mu2 are coefficient of frictions at different surfaces, and beta 1, this alpha is the semicone angle between uh, you know die, semicone angle of die, and this is semicone angle of plug or mantle, because in tube drawing you use that to make the hollow center. Mu1 will be mu between tube and die. Mu2 is frictional coefficient between tube and plug. Yeah, so the formula resembles same or similar structure, but instead of B you have B dash, and this B dash definition changes. This much you have to remember. So far, tube drawing question has not been asked in GATE exam, so don't. I mean, it depends on how you take it. They may not ask it, or they may even ask it. So like that. Okay, so that is about tube drawing or drawing in general. Then you have some drawing defects. Let me just see. Okay. And we have this sheet metal operations like punching, blanking, all those things. bending, all those things are there, and then the defects. So let me just see. See these forging effects, etc. Or what I'll do, maybe I'll discuss those things in the end. So let's discuss about this some of these important sheet metal operations, and maybe bending or something like that. Okay. So when you have this punching operation, right? Punching or blanking. Uh, let's discuss that part because sometimes they ask questions from that also. Okay. Hmm. Yeah, let's discuss about punching and blanking, which comes under different sheet metal operations. So punching and blanking. Physics wise, no difference because both of them can be done on the single machine. It's just that punching, uh, you, for example, if you have a sheet like this and if you punch it, let's say a hole in it, if this is useful part, if this is useful part, then it is called as punching. But the hole that you make out of this, if this is useful part, then it is called as blanking. That's it. That is the difference. Nothing major definition wise. Okay. And so basically what happens in these operations, the simple schematic can be drawn like this. So you'll have die. So this will be your die. So die, and you'll have a punch like this, which will come here, and it will shear this this. Oh, sorry, the die is not there. Die is at the bottom actually. So this is your workpiece, and die will be somewhere here. So I mean, this is your workpiece. Die is nothing but to provide some support like that. Okay, so die for support, and then you have this punching operation. Okay. So in blanking, usually you get uh, discs like output, and here you'll have holes in your this thing. But the difference is, and it is asked in many competitive exams, about the clearance. Okay, so you should remember that in punching operation, the clearance is provided on the die. What I mean by that is, if you want to punch a hole of diameter d, then die, uh, you know, die dimensions or die hole dimensions will be, let's say capital D is the die, so that will be hole diameter plus 2c, where c is radial clearance. So if it is a diameter clearance, then you have d plus c. So what I mean by that is, uh, let's say you have this workpiece like this, and if your punch dia, which is equal to the whole dia, this is your small d, then your die will be supporting the part, let's say this part, and but you have to keep slightly extra clearance for punching. That clearance is provided on the die. Whereas uh, in case of blanking, the clearance is provided on the punch. Okay, and what I mean by that is, if you want, let's say you have this specimen or workpiece like this, and if you want to take the out of this, you want to take the disc of let's say diameter or dimension d, capital D. So this will be your dimension, and that will be equal to the disc dimension, capital D. But your punch will be smaller in this case. Punch will be D, and D will be D minus 2C here. Okay, so clearance is provided on the punch. So this is a very important MCQ question for competitive exams. And sometimes C is, or the radial clearance is not clearly mentioned. If that happens, then there are two ways to calculate C. C is calculated as 0.0032 thickness of the specimen into square root of the shear stress or shear strength of the workpiece, or C can be taken as 3% of the thickness. Okay. So usually it is given in the question, but if not, then you have to assume that uh, this thing, what you say, 3% of your thickness of your specimen. So thickness is the specimen thickness. Okay. Mostly it will be given in the question, but if not, then you can assume this way. And then typically you don't go all the way. So if you want to have the punch of thickness T, you don't traverse with the punch whole way, because you are spending energy, right, for punching. So you only travel up to some penetration. Okay, so because after that, because of fraction or fracture, uh, that shearing takes place, and you'll have your desired output. So you need not have to travel the whole thickness of your specimen, and that is called as penetration or penetration factor Ka. It is nothing but divided as ratio of distance travel or traversed by punch into the sheet metal divided by, and till complete detachment, divided by thickness of the sheet metal. So this penetration factor, usually it should be less than 1, then only it is beneficial for us. So this work done, or so the work done required for punching will be nothing but F max into KT, where F max is the punching load, and that is calculated as ultimate shear strength of the material into perimeter into thickness. basically this perimeter into thickness and into KT. Okay. So perimeter depends on what kind of punch you want. If it is a circular one, you'll have pi d perimeter. If it's a square, you'll have 4a or something like that. Okay, but what happens in reality, right? You'll not have punch with the flat surface, because when you have punch like this, you know, so if you have a flat punch, so this is the example of flat punch. So in that case, here the problem that happens when you have a contact with the workpiece. Okay, let's say this workpiece is like this. So here, you know, on this surface, you'll have a high stress concentration. Okay? Because the whole load is distributed over the surface, so you'll have higher stress, uh, you know, higher stress on the punch surface. So what they do typically to avoid this, they provide some shear. So instead of having, flat uh, this thing punch, you usually have some incline. Not necessary to have like this. Ideally, it is something like this. If you see the actual punch holes or punches, it is actually symmetric about central axis. So you'll have punch like this. Okay, so this will be your center axis like this. What happens here? Uh, this point will be first in the contact with the uh, workpiece or the punching material, and then the contact length gradually increases, and then you have the full contact with the punch. Okay, so this height, this height is called as the shear, which is in S in mm usually. Okay, so this shear helps to basically uh, you know load on the punch is reduced, but it does not mean that you need lesser energy, right? So for same energy requirement. So it's not that if you give the shear, uh, the energy requirement reduces. The load on the punch reduces, which increases the punch life. Okay, so that is the advantage of providing shear, not the energy. You don't have any energy savings by providing shear. You only improve the life of your uh, punch. Okay, and then you can do this energy balance, right? So initial energy balance was F max into KT, and let's say finally after providing shear you have F, which is K, F is actual force after shear, that becomes KT plus S. Okay, and therefore you have F, which will be F max into KT by KT plus S, and this ratio is less than 1, therefore the force required will be less than the the maximum force, assuming, uh, inner this energy remains same, but the force comes down. Okay, for example, if K is, let's say, 50%, so you are traversing only half of the thickness, and let's say you provide the shear which is equal to T. In that case, your F becomes F max into K is 0.5, T is T, 0.5 T plus S. S is actually equal to T. So in that case, you actually need to provide only 1/3 of the punch load. So that means 67% reduction in the punch load. Yeah, so that's a significant one, right? So this is the advantage of providing shear, etc. And again, if you are doing, so take it as a note. So far we have seen for punch, right? So for punching, shear is provided on the punch, whereas for blanking, shear is provided on the die. Okay. Okay. And then there is another uh, this thing which is called as uh, minimum diameter of hole. So for a given punch, you cannot have infinitesimally small hole diameter. Minimum diameter of hole that can be punched for a given punch, there is a limit up to how you can go down. So that is calculated by simple energy balance, which is load exerted by workpiece on punch. In limiting case, it has to be equal to crushing strength of the punch. Okay. And if you do that, this will be the tau ultimate of the workpiece into perimeter into thickness. And crushing strength of the punch, it's a material property, it will be given in the question, and it will be acting on this pi d square by 4 area, right? So that is the minimum this thing. Okay. And this is assuming no shear on the workpiece or the punch. Okay, so if you have shear, then this LHS will be modified, like because where is it? Yeah, you have this what is the formula? Punching tau ultimate into pi dt, right? So F max is this tau into pi dt. So if you have shear and all, so F will be again this value you have to use. Okay. And yeah, sometimes see, sometimes if you don't know the tau ultimate, sometimes what they do, they take it as equal to 70% of ultimate tensile strength. Sometimes, I mean, not always, but sometimes. This was also discussed in the class also. But if you know the shear strength, that is well and good. If not, then take like 70% of the ultimate tensile strength. And from here, and this will be also d minimum, and therefore you get d minimum. So this is the minimum hole dia that can be punched for a given punch. It comes out to be 4 tau u into t by sigma c. Okay, so this is the formula for that minimum hole that can be punched using some given punch. And for safety, usually d has to be greater than d minimum. Okay, otherwise your punch will crush. Okay, so like that. And here you can see one thing, from this formula itself, d minimum increases as sigma c decreases, right? Or vice versa, because when you have higher crushing strength for the punch, you can have smaller holes also. And another way to have smaller holes is, you know, increase the shear strength or shear strength of your workpiece, or increase the thickness of your workpiece. But typically we don't do this because, in that case you need to provide more energy. So typically this is not the good way, this is the way. So basically, if you can, you should have a punch with higher crushing strength. That is the case. And sometimes what happens, apart from minimum clearance, you have some allowances. So along with radial clearances, some additional allowances are given. So in some questions, if you see something like this, then no need to worry. Basically, you have to write again for punching and blanking separate, so that that for punching you provide clearance on the die, so that will become D plus 2C plus whatever allowances you have. And for blanking, it is provided on the punch. So yeah, so this D will be D minus 2C plus allowance. So just a precautionary note, because in some cases they'll not mention those things. Okay, so this is about this thing. Then you have this something called as a drawing operation. Anyway, we are running out of time, so we'll quickly discuss the important formula, because defects and all, they are already discussed in the class. So rolling, forging, all those defects, even some other defects, and today I have given you the extrusion defects also. So you can go back and you can refer any standard book. The defects are very well known. So we'll see some problems or the formulas for some problems, so that if you see something, you'll be able to answer. Okay, so yeah, a couple of formulas are remaining, so we'll finish those and then we'll go to the next one, or we'll finish the class. Okay, so for the drawing operation, see, drawing is nothing but a process for making cups or something like that, glasses, something like that. So in here, the main thing that you should remember always is, you don't go up to the ultimate shear stress or shear strength of the material, because otherwise you'll have punching or blanking. Here you don't go up to that, you just want to deform something, and that is achieved by blank holders and all. So here you'll have a specimen like this, you'll have blank holders like this, they will hold your specimen with some pressure, and then you apply the punch, and then you finally get the product, something like this. This is how it goes. So here additional thing is blank holders. So these are blank holders, and you have to understand one thing. You have some blank of, let's say, capital D dia, or yeah, let's say capital D dia, and you make a cup like structure out of this, of let's say small d dia and height h. Okay, after drawing operation. So in that case, uh, you know the volume has to be constant, right? So one thing that you can assume is, assuming same thickness, so the blank thickness and the cup thickness are same. In that case, you can write pi by 4 d square equal to pi dh, which is the bottom surface area, curved surface area, into pi by 4 d square, right? This is assuming same thickness of blank and the cup. So you have this relationship between these various D and H. And it is observed that when you have uh, these kind of drawing operations, you should have some corner radius on the punch or on the design itself, because otherwise there will be some crack at the edges. Okay, so cracks may be developing in these regions, right? So you need to have a corner radius, and for corner radius, you have some thumb rules. Corner radius R, so you have some thumb rules for that. So if this d by r, so final dimension or final diameter of the cup divided by r is 20, in that case you can have this, the blank should be of this much diameter. But if this is between 15 to 20, then the blank diameter needs some correction for that given corner radius. The first part remains as it is, but you need to subtract 0.5 times of r from this diameter. Okay, this is about corner radius. Then you have drawing is called as divided into two parts: shallow drawing and deep drawing. And how do you bifurcate amongst these two is, if h by d is greater or equal to 0.5, it is called as it should be less here. Yeah, if it is less, then it is a shallow drawing. But f by d is greater than 0.5, it is deep drawing. So basically, you have higher heights than the diameter. So this is there. And yeah, sometimes they ask this compression and tension kind of questions. So let's say you have flanges like this. Okay, and you have this cup holder at the bottom. So inside it will be hollow. So this flange, it will be under compression or plus tension, because compression comes from the uh, blank holders and tension comes from the punch stretching, whereas this wall or cup wall, it will be only in tension. So these kind of questions are also asked, so I'm just giving you some hints. And what happens sometimes, it is not possible to have complete edge kind of depth achievement in one draw. So therefore you can have number of passes also. So then it depends, like percentage reduction in diameter in a draw. So this is like similar to our previous cases. So percentage reduction in the diameter per draw is nothing but 1 minus d by d into 100%. Okay, so and you know uh, in some problems you may see drawing process is also called as bending plus stretching. Okay, so sometimes it is also called as combination of bending and stretching. And there is something called as draw ratio. Draw ratio, which is defined as d by d. And then there is something called as limiting draw ratio, which is defined as LDR. So LDR is the maximum of blank for which you can have d diameter. So draw ratio usually should be less than this, but what happens if d by d is greater than the LDR? In any cases, you will not have a drawing operation. In that case, what happens? The punch will pierce a hole in the blank. Okay, so therefore this LDR is basically a limiting case, and you have to always stay within that limit. Okay, so this is mostly about the this thing, drawing as far as questions are concerned. Then next operation is called as bending, and bending, again, as we discussed earlier, bending is nothing but, again, this compression plus tension, because one surface will get compressed, one will get stretched. That will happen during bending. And there is very important question sometimes asked directly in the exams, something called as bend allowance. Okay, so this will be your neutral axis while bending. So what happens, let's consider this is the domain of the bending. So if you have theta, which is the bend radius, angle of bend, and this is your r, which is bend radius, in that case, bending allowance is calculated as theta into r plus kt, where kt is called as stretch factor. Okay. And this type of questions are directly asked in the exam. And this is for one bend. If you have multiple bends in your forming process, then accordingly you have to add multiple bending allowances in your total length. Okay, so we can take one question also. Yeah, so the question is again previous year gate question. So they have mentioned as 2 mm thick plate is there, or sheet is there. Okay. And theta is given as 1 radian, capital R is given as 100 mm, stretch factor is given as 0.5. What is the bending allowance? Okay, and one thing is this theta is always in radian, not degrees. Okay, not degree. So this kind of straightforward questions are asked. So this, in this case, this will be just theta into r plus kt. Oh, sorry, this kt is k into thickness. So the stretch factor is just k. Okay, so like this. So it is already in radians, so no need to convert. 100 plus 0.5 into 2. So therefore 101 mm. Okay. So this is how you have to solve some numericals if they are asked. And the final thing, and we'll stop after this, is called as spinning. So there is a formula in spinning. So spinning operation, again, this lids, if you have metallic Tupperware kind of things in your home, the lids, they are typically without threading, the lids are there, though they are prepared by spinning only. So what they do is, typically you'll have a rotating cone like this, or maybe not cone but kind of a shape like this. This will be rotating about its natural axis, and then it is pushed through a sorry it is pushed through a specimen of certain thickness, and this specimen is actually pushed using some rolls or something like that. So finally you'll get shape like this. Okay, something like this. Forgive my drawing, but I hope you get the idea, because when that hole pierces, or the pushes inside this sheet, so finally you will get the product as like this. Okay, so something like this you will get, and this is called as spinning. So here one important question asked is about if this is your initial thickness, let's say T, what will be the final thickness? Let's say TF. What is it? So that is kind of the question. So here, you know, this is called as mandrel. Okay. So what they do typically here is, and this will be some angle like 2 alpha we had now previously. So this is also 2 alpha. So there will be some semicone angle. So alpha is your semicone angle. So you have something like this. So this will be your initial thickness T. This will be your semicone angle alpha. This will be your final thickness TF. So from trigonometry you can write your final thickness is nothing but T into sin alpha. So sometimes this kind of questions are also asked, okay, from spinning. And spinning is also again compression and stretching and tension, everything is there. So yeah, then there are different types of forming processes, but we'll not go there because not required. Okay, so okay, so yeah, this is like more or less the end of the discussion. Sometimes they ask the question, in case of drawing operation, they will give you the cup dimensions which are observed after the drawing. So diameter and height will be given, and the thickness of the cup is also given. So you are expected to find the blank radius. So you can use that d square plus 4dh formula, assuming same thickness for cup and the blank. And then they will mention that if you have 2-3 passes, how much reduction we observed in the diameter, like that. Okay. So that's how. I think you can solve those questions because we have done similar questions previously. So with that, we'll stop for the day, and we'll meet in the next class, and we'll discuss. I think we'll start the welding. Okay, so maybe I'll just So this image was looking pretty bad, so I'll just cover up my bad drawing with this kind of thing. Anyway, okay, so this is the end of the class, and yeah, see you next time. Bye.